All right, so let's look at this. So this is a free response style question that if you can start understanding how these questions are worded, this is going to be very much how some of our tests are going to be worded. So if you're needing reading comprehension skills, we need to work on those things because this is very similar to what you're going to see. Okay, an experiment is performed to determine the empirical formula. So here's my thing. We see all this junk and it freaks us out, but if we read it, that's what we're trying to get, right? So I want you to find those words that you know, and you're like, and really just kind of see what they're doing, and don't let it freak you out because they're going to throw a lot of pictures at you, they're going to throw a lot of words at you, but when it boils down to it, it's still chemistry. No matter how they ask it, chemistry is behind it. Okay? Of copper iodide. Now, I want to think about this for just a second. So would you agree if we wanted an empirical formula, we could say CuXIY? Is that true or false? True. Now, does copper always have the exact same charge? No, because if it did, would this be a really easy problem? Yes. Well, the problem with this is copper is a transition metal, therefore it has multiple charges. What are copper's only charges? Okay? 1 and 2. So hypothetically, this empirical formula only has 2 potential results, correct? Okay? What are the 2 potential? Very good. CuI or CuI2. That's it. There are no other options for this entire formula. That's it. There's no other options. So we got to figure out how to figure out which one it is. So copper iodide is formed directly by the combination of elements. Now, what does a combination of elements mean? Okay, we're literally going to take copper and we're going to add it to what? Now, true or false? False. Why? Very good. Iodine is a diatomic. Now, here's another really, really, really tricky question, and this is really important. Now, we all know copper at room temperature is what state of matter? It is a solid, and this is a weird one that a lot of people forget. What is the state of matter of iodine at room temperature? What color is it up there on that back left periodic table? You can see it the best on that one. It's black, but look at the rest of the halogens. The first 2 are, which are gases, and then bromine is a liquid, and then iodine is a solid. So that's interesting. All of a sudden, we get to iodine, and it turns into a solid. There is a reason, and we will get to that reason later. I'm wanting you to make an observation at this point. Okay? Yes, sir. It is iodine. No, it's not. Okay. And medical stuff. Yeah. It's a swab. It's a solid. It's not a liquid. It's just a swab. Okay? All right. So, this is the issue. We've got to figure out how to deal with this. We've got copper metal, and we're going to put it in, we're going to react with iodine. Now, if these 2 things didn't react, could we ever have copper iodide? No, so they have to react. True or false? True. Second question is, iodine actually goes through the process of going straight from a solid right into the gas. What is that? Sublimation. Okay, so iodine actually sublimizes. Now, a clean strip of copper metal is weighed accurately. Now, let's look on this data table. To what degree is it accurate? 5 significant figures, but to what decimal place value? Tenths, hundredths, thousandths, 10,000ths place, right? Is that pretty accurate? Yeah, that's real accurate. Okay. Now, it is suspended in a test tube containing iodine vapor generated by heating solid iodine. So let's try to visualize this thing. First of all, we got a test tube, right? Okay. So at the top of this thing, I'm going to use a dark gray color. There's this stuff called paraffin. Okay. Now, if you had this stuff in your kitchen, you would love it. You want to know why? Because it's saran wrap that doesn't stick to itself. You know what I'm talking about? Like if you pull, like that clear stuff, if you tear it, it just clings to itself and you can't ever get it back apart. So what paraffin actually is, it's the same stuff, it's a little bit thicker. But what you can actually do is like, let's pretend you had like a glass bowl. If you took paraffin, you could stretch it around it and seal the top, and it seals, like it sticks to it. Like, paraffin's some really cool stuff. So, bingo. That's exactly right. I agree with you. It's just, no, it's not expensive. It's new technology stuff. So we're not worried about that. Just stay with me. So here's the deal. So in the bottom of this stuff, okay, we've got these I2 solid pellets. Okay, these I2 solid pellets, and it tells you. And we're gonna use let's use a brown string, and this is kind of okay, it's just kind of a loop, and then tied to this thing is a piece of copper solid. So this is essentially what's happening. It's suspended through. Now you can either poke a hole through the parafilm and run it through it, or you can just drape it over the side and seal it with the parafilm, however you would want to do it. But eventually what happens is underneath this thing, what are we going to have? Flame. We're going to have flame. So we can add all this flame in here, but we need really what? We need some blue flame, right? Okay, get it real hot. Well, when this thing starts to heat up, what process does it go through? Sublimation. So what's going to happen is this stuff is actually going to start to vaporize. Okay? So it's actually going to start vaporizing. What's going to happen is it's going to start reacting. So this copper, okay, this copper plus I2 makes CuXIY. Okay, it actually reacts right there on the surface of the copper, and so I'm just going to make that a yellowish color. Now, I mean, I really don't know what color it would change it, but we're just going to pretend that it reacts and changes. Perfect. Well, then you can't draw white, so we'll go gray. Pretty good shading, right? Okay, yellow base, a little bit of gray underneath it, and then a white. So I'm glad you actually read ahead of that. So visually, does this help? Okay, so that's kind of what's going on there. All right, so let's go back and look. So a clean strip of copper metal is weighed accurately, suspended in a test tube containing iodine vapor generated by heating solid iodine. A white compound forms on the strip of the copper, coating it uniformly. Now, this word really doesn't mean a whole lot, but it kind of does in terms of a scientific purpose. What does it mean by uniformly? It's all smooth, okay? So it's not kind of like bulky. It's all smooth coating, okay? The strip with the adhering compound. Now again, what is this compound? Very good. It's this CuXIY. It's that thing. Is weighed. Now, the strip with the adhering compound is weighed. Finally, the compound is washed completely from the surface of the metal, and the clean strip is dried and reweighed. So essentially, what did washing it do to the strip? Okay. It got rid of the reacted copper, right? So what we washed off was essentially what? Okay, the copper iodide was washed off. Okay, so let's look. We have the mass of the clean copper strip. We have the mass of the copper strip and the compound, and then the mass of the copper strip after washing. Does that make sense? So here's my first question. Can we determine how much copper reacted in this? Very simple. How? Subtract. So let's do that. So the first thing we're going to do, my first question, is what are we going to subtract to determine the amount of copper that reacts? Okay. All right, so we're going to do clean minus AW after washing. So 1.2789 grams minus 1.2748 grams, which gives us a grand total of 0.0001 grams of copper. Does that make sense? Now, the next problem is we got to figure out how much of that was iodine. So how do we figure out how much iodine was there? Okay. So we've got clean copper, and then we have copper and the compound. So what was the only thing added to the copper? The iodide. Very good. So what we're going to do is we're going to say the Cu plus the I2 minus just the Cu. All right, so that's going to be 1.2874 grams minus 1.2789 grams gives us 14 minus 9. Hold on. Hold on. 5. Help me out. Yeah, you got to borrow. So that's a 6. So then make it 16, so 8. And then make that a 7, so that's 0, right? Is that right? Sounds good. It's been a while since I've done that. I'm so glad. So here's the deal. So hang on. What we have just done is we have figured out how much copper from the original copper mass came off the thing, and we have figured out how much iodine reacted with said copper. Okay? Nicole, now ask your question. I understand that. However, I'm one of those that this is where I was going. I was fixing to read the question. So the question says state how you would. Now state means a statement or words, correct? Do you agree that by showing them the actual mathematical calculation, that is proving that you know exactly what you're doing? Okay? So even though you don't use words per se, in a way, now obviously if we were doing this properly, I would have done a much better job of labeling that, and I would have done a much better job of labeling that. So if you do those two things along with the numbers, you are guaranteeing proof that you know what you're doing, not just by words. If you, like I said, these two green circles, if you had labeled them more accurately, like you said, the clean copper strip minus the after washed strip, and then did the numbers. So I kind of shorthanded the important part, and I went straight for the data. But they can look at this and know exactly where your numbers come from. We would just want to label the two green circles a little bit better. Yes, ma'am. In fact, I would encourage it, because I'm going to be honest with you. If there is some sort of tell me what you did question, the new style questions, I'm willing to bet that there's somewhere in that question following it up, you're going to need those numbers anyways. So go ahead and do it. Sir. Yeah. Okay. Why? Okay, whatever wakes you up. So it says, state how you would use the data above to determine each of the following. And then it says calculations. Now notice what it said. And Nicole, this is important. Not required. But did it say illegal to use? Not required means you don't have to show the numbers, but I'm one of those, I'm a numbers guy. Numbers make sense to me. I would much rather put it in numbers than put it in words. Okay? Because also, does this prove that, like, okay, logically I know where this stuff came from, numbers-wise? Hold that thought. That's where we're going next. Yes? Yes, ma'am. You and me now? Okay. Now, what Mason said is important. If we left it like this, we technically did it incorrectly. The reason why is because the question number A1 says, state the number of moles of iodine that reacted. So you could do this. Now, could you continue to calculate? Sure, but you wouldn't have to. What could you then say under the right writing in red? Okay. You would convert the grams to moles, and this is the important part that some of you probably left out. How would you do that? Divide it by what? The molar mass. Why would you not need mole to mole ratio, Trevor? This is important. Exactly, and you're in grams. Okay. The question is, how do I get to moles? So you would divide the I2 by the appropriate molar mass. If you did not write that, you need to write that. You would divide the mass of the reacted iodine by the appropriate molar mass. If you said convert grams to moles, I don't know what grams you're talking about, and I don't know what moles you're talking about. Okay, but you're telling me what to do, not how to do it. If I told you convert grams of iodine to moles of iodine, you told me what to do, right? But you didn't tell me how to do it. If I then told you by dividing by the appropriate molar mass, is that how to do it? Yes, and that's the important part that I need to make sure that you guys understand, is there's not just a what to do, it's a how you're going to do it, because read the question. And Mary Beth, I think this will make more sense when you read it. It says state how, that's the wrong button, state how you would use it. Not what to do with it, how to use it. Okay, now, A2, and you probably left this off as well. It says the number of moles of copper that reacted. Do you agree we already have the grams of copper that reacted? But then what must you do to get it to moles? Divide it by the appropriate molar mass. Now, if you wanted to be intelligent, you could say, you could actually put the mass of copper in parentheses, which is 63.55. If you wanted to throw that in there for a little bit of extra substance, cool. If you wanted to on the other one double the mass of iodine, which is 126 times 2, you could, but it's not required. It is a lot. It's very heavy. All right. B. Explain how you would determine the empirical formula for the copper iodide. I hope it went something similar to this. My first question is in A, have you already established the number of moles? So do you need to mention getting it into moles? You've already got that. Okay? You're already in moles. You would then do what? Divide by the smallest number of moles. Or empirical formula. Okay? Then you would want to make sure that your values are within 1/10 of a whole number, correct? And that would be your subscripts to your answer, true or false. True. Now, this question was 1990, question number 9. Now, there's not 9 questions anymore. There's only 7. Okay? But this was 1990. This was the exact question they gave that year, number 9. And this is how they scored question B. This is what it says. The empirical formula is the ratio of mole of iodine to mole of copper. That's their answer. Or alternatively, mole of copper to mole of iodine. But what you said, did it relate the two things? Did it give you the smallest number of moles, and then you said make sure your numbers are within 1/10 of a whole value, and those are your subscripts? Is that not a mole to mole ratio? Yes, that's essentially what you're trying to do. Okay? Does that make sense? All right, now looking at C. Explain how each of the following would affect the empirical formula that could be calculated. I'm telling you now that these style questions are becoming very, very, very rampant on the AP exam. They give you all this stuff, and at the very end they say, well, what happens if we change this? What happens? If we do this, how does it affect this? If we do this, how does it affect that? These questions are becoming very popular again. They used to be popular, they kind of went away, and now they're coming back. It's an analytical thing. You actually have to think, okay, if this happens, then this happens, then this happens, then this happens to get to your result. Some of them are very straightforward and pretty simple, but some of them are very complicated. Okay? So let's look and see what it says. Explain how each of the following would affect the empirical formula that could be calculated. Some unreacted iodine condensed on the strip. Very good. So what is it technically adding to? Which part of the data table would it affect? Okay, it's going to affect that thing right there. So now you can't just say, oh, well, it affects the mass of the amount of, it affects the amount of iodine reacted, because here's the important part. Whenever we're talking about relationships between elements or compounds, what unit do you have to compare them in? What unit do you have to compare things in? Moles. So, yes, the amount of iodine will be affected, but which amount? The moles. Would it increase your moles or decrease your moles? It would increase your moles. So you need to have something in your answer about increasing the number of moles. Can I read you the answer? It said unreacted iodine would make the apparent mass of the compound and the iodine too high. Thus, the copper to iodine ratio would be, in the empirical formula would be too high. And so here's the part that you probably left out. Let's read the question. It said, explain how each of the following would do what. And this is the key part that students do not read. What is the question? Can you just talk about the iodine? You must mention something about the empirical formula. So if one of the ratios goes off, is it going to affect the ratio to each other? Yes. That's what you have to mention, is something about to the effect that the ratio of copper to iodine would be affected. Therefore, would it affect the formula? Yes. Because really, what is an empirical formula? It's a ratio of atoms to atoms. And in this case, what two atoms are we talking about? Copper and iodine. Does that make sense? It increases, it alters the ratio of copper and iodine. Because think about it. If think about it this way, Madison. Follow the color change. If this changed to 1.2890, did that number go up or go down? It went up. So would you agree that you would say that your amount of iodine would also go up? Well, if your amount of iodine went up in grams, did it go up in moles? Okay. Well, when you divide it by the smallest number of moles, could it affect what your smallest number was? Then would it affect your ratio back and forth? So does that kind of make sense? Okay. And sometimes it just takes looking, okay, if this number changes, what all does it affect? And a simple little bit of just unreacted iodine sticks, it throws the whole thing off. That's why it's so important that we pay attention to the details. All right, 2C. A small amount of the white compound flaked off before weighing. So basically what that means is, if we went back to this drawing and some of this white compound actually fell back off, what would that then thus affect? No. It would affect the second one. Okay? Because after you washed it off, hang on me. All right, it would affect, if some of the flake, the mass of the compound and the iodine would be too low, right? Thus, the ratio would also be off. Okay, the ratio would be different because you don't have enough of the reactant species. Does that make sense? We good? So do you see how very in depth some of these questions can become? Yes. You just hold that ball game because it gets a lot more crazy. All right, so number one. The following, which provides the most acceptable name for Fe2C2043? Okay. Iron 3 oxalate. This is oxalate. You reverse crisscross, you get 3 plus, 2 negative. Is oxalate 2 negative? Yes, it is. Okay. All right, suppose an element consists of 3 naturally occurring isotopes. The reported average mass for the element was 75.42 AMUs. Now, this is the average mass that you would find on the PT. Now, is there a mass that is actually on the PT that is that amount? No, there is not. Okay. The following information known. Isotope 1 has a mass of 80.45 and makes up 2.4% of the element. Isotope 2 has 72.22 and makes up 30% of the element. What do you estimate the mass of isotope 3? All right, so let's look and see how we can figure this out. So, do you agree that it's iso times percent plus iso times percent, times, let's actually do it a little bit easier. All right, so it's the iso, come on now, play nice, mass times plus And I'm telling you now, this is going to be one of your multiple choice questions. And it all equaled what? Help me out again. 75 point what? 42. So, now, they tell you that the mass of the first one is what? What? I hear two different numbers. The first one. And what's this percent? So which is what? 0.24, right? No, that's wrong. 0.024, right? Okay, plus what's the mass of isotope 2? And what's this percent? Even? Okay. And then the last one they ask you about is what? The mass of isotope 3, right? So X times... Uh-oh. We're missing two things. Or are we? Can you find a percent? What is it? All percents have to add up to be what percent? 100. Okay? So, what is 100 minus 30 minus 2.4? 67.6%. Would you agree with that? Does that make sense? Now, can we write it in just as it is? No. So, 0.676%. Now, if you were in 8th grade math, did this turn into a really easy problem all of a sudden? But the way that it's worded is a little bit more challenging. Now, so what would you do right here? Multiply. What would you do right here? Multiply. What would you do right here? Multiply. So you would end up eventually with 0.676x. Now, what would you do with this value and this value from the red number? Subtract it from the total, right? Then once you subtract it, what would you do with the 0.67x? Divide. So what would your x value be? 74. But does that make sense? Okay? Yes, no, maybe. But does this make sense? Yes, ma'am. This is the best, this is really the accurate way to do it. $67.6. So you did it a roundabout way of this exact same way. This is just this is the proper setup. Okay? Alright, now, and I'm going to be honest with you. If you're taking a multiple choice and it sounds, go with your gut if you don't know exactly how to do it. Try to find something reasonable. Alright? Number 2. Consider a diamond in a jewelry item that is only made of one carbon atom. Okay? If the diamond has a mass of about 0.2 grams, how many atoms? Consider that a diamond as a jewelry item is only made of one carbon atom. Yeah, that's a stupid entry. So here's what they really wanted you to do. They wanted you to go from grams to atoms is what they wanted you to do. Okay? All right, so 0.20 grams. Now, if we don't want grams, what do we go to? Okay? Now, we always can go to moles. Now, my next question is, if we have moles, can I go from from moles to atoms? Yes, you sure can. All right. So now we're talking about carbon, right? All right. So in 1 mole of carbon, how much does 1 gram, or how much is? Okay. So we've got 12.01, and in 1 mole, how many atoms are there? Very good. It's a 6.02 times 10 to the 23rd. I'm assuming this is probably going to be number 3 to the 22nd power. Dustin, yes? Okay, so it is. Because I know that 0.2 times 12 is going to be a really small number. And it's going to pull that, because it's a decimal number, it's going to pull that down 1. 0.2 times, you got an 89. I don't do 89s. Calculator you got right there, it's that bottom button where it says EXP. 6.02 EXP 23. Did y'all not have to do that last year? Number 3. Stay with me. Stay with me. The compound Cr2O3, chromium 3 oxide, is one of the key components responsible for the red color of ruby gems. If you had 34.8, stay with me. Hang on, Dustin, wait for just 1 second, okay? If you had 34.8 grams of that stuff, how many grams of chromium would you have? Now, this is important because we're going from chromium 3 oxide to what? Chromium. So you remember we need that atom to molecule ratio, right? Atom to compound ratio. So if we've got 34.8 grams of Cr2O3, we can say grams of Cr2O3 in 1 mole, right? Okay. Now, this is the next part. So in mole of Cr2O3, we can have moles of Cr. True or false? True. This is an atom to compound ratio. What is the bigger one? The compound. How many Crs are in that thing? 2 of them. Now, I messed up because I made my stoichiometry too big, but could I stop right there based on the question? What's the question? Grams. So what would I do? Convert. So in 1 mole of Cr, there are 24 grams of Cr. Did anybody get the molar mass of the chromium 3 oxide? That's the answer, but what's the molar mass of the chromium 3 oxide? Well, then how did y'all get the answer if you didn't? Okay. Okay. Well, duh. Chromium is 52 even. Chromium is 52 even. So 108 plus 96, or 48. What? Okay. That's what it is. 104. My bad. Where did this come from? Oh! My bad. Thank you for catching that. That was a big mistake. Thank you, Mary Beth. That was what number to look it up by. The mass is 52.